1. The corona's extreme temperature, coronal heating problem. The surface of the Sun, photosphere, is about 5,500 degrees, but its outer atmosphere, the corona, reaches temperatures of 1 to 3 million degrees C. At first glance, this seems paradoxical. Shouldn't it get cooler as you move away from the heat source? Scientists are exploring two main theories. Magnetic reconnection. The Sun's magnetic field constantly shifts and reconnects, releasing massive amounts of energy that could be heating the corona. Alfvén waves. These are magnetic waves that move through the Sun's plasma. They might carry energy upward into the corona, but how this energy is absorbed and turned into heat remains a mystery. Solving this problem could improve our understanding of stellar physics in general. 2. The origin and dynamics of solar wind. The Sun constantly emits a stream of charged particles called the solar wind, which interacts with Earth's magnetic field and creates auroras. However, we still don't fully understand where exactly the solar wind originates, how and why it accelerates to such high speeds, why its intensity varies dramatically over time. Coronal holes are suspected sources of high-speed solar wind, but the process is not fully understood. These winds can disturb satellites, navigation systems, and even power grids on Earth. 3. Magnetic field reversals and the solar cycle. Every 11 years, the Sun flips its magnetic poles, the solar magnetic reversal. This is closely tied to the solar cycle, during which the number of sunspots and solar flares rises and falls. Changes in the Sun's activity that influence space weather, affecting satellites and communications on Earth. What causes the solar cycle to be so regular, and how the Sun's magnetic field organizes itself so consistently, are still not fully understood. 4. The Sun's internal structure and core dynamics. In the Sun's core, nuclear fusion reactions convert hydrogen into helium, releasing immense energy. However, we cannot observe the interior directly. It's opaque to electromagnetic radiation. Instead, scientists use helioseismology, the study of vibrations on the Sun's surface, to infer what's happening inside, similar to how seismologists study Earth's interior with earthquakes. Unresolved questions include: how exactly is energy transported from the core outward? Are there gravity waves inside the Sun? How do large-scale convection currents behave? 5. The Sun's future evolution and final fate. The Sun is around 4.6 billion years old, roughly halfway through its life. In about 5 billion years, it will exhaust its hydrogen fuel and go through dramatic changes. It will expand into a red giant, possibly engulfing Mercury, Venus, and even Earth. Then it will shed its outer layers and leave behind a dense white dwarf core. However, the details of this transformation, especially the fate of the planets, are still being studied. 6. Sunspots and solar flares. Sunspots are dark, cooler areas on the Sun's surface associated with intense magnetic activity. During solar maximum, their numbers increase, often leading to more solar flares and coronal mass ejections, CMEs. These flares release massive amounts of energy, more than billions of nuclear bombs, can disrupt satellites, radio communication, and even electrical infrastructure on Earth, pose radiation risks to astronauts and space missions. Despite advances in solar monitoring, predicting when and where these flares will happen remains extremely difficult.